In this video, we're going to introduce the concept of optical isomers, so that's a new type of isomer that we haven't discussed yet in this class, and we'll also talk about chirality. Now, in order to visualize this, I think it's going to be important to show some models, and so in just a moment, you're going to see the camera pop in, and I'll be on the screen showing some models of some molecules. So first of all, what are optical isomers? Optical isomers are molecules that are non-superimposable with their mirror image. Now, I recognize that that's kind of an abstract thing, so let's think about a real-world example first of all, because there are a lot of real-world cases of things that are non-superimposable with their mirror image. A real-world example of something that's not superimposable with its mirror image would be our hands. The right hand and the left hand are mirror images of one another, and these are non-superimposable with one another. So just to get an idea for this, imagine, right, I've got my right and left hands here, and when I overlap them on one another like this, yes, my thumb and my thumb line up, my pinky and my pinky line up, but this hand is coming out towards you, and this hand is going away towards me. So I could try to make my hands go in the same direction, but now when I do that, now my thumb on my left hand is overlaying with the pinky on my right hand, and vice versa. So this is not superimposable. And no matter how I twist and turn my hand, I can never make my hands point in the same direction with all the fingers being in the same locations. These are non-superimposable objects. And molecules can also have handedness like this. For an organic molecule, optical isomers will be possible if you have what's known as an asymmetric carbon or a chiral carbon. In order for a carbon to be asymmetric or chiral, it has to be attached to 4 different groups or 4 different things. We can take a look at an example here in the slide, but I think that it's also helpful to see a real model of it. So in the slide, I have a carbon that's attached to 4 different things and its mirror image, but also I've made a model here of a carbon that's attached to 4 different things and its mirror image. So I've got a carbon atom that's attached to a red, a white, a brown, and a blue. 4 different things that it's attached to here. And these are mirror images of one another, right? They overlay with one another. White goes into white, brown goes into brown, and so on. Now, these molecules are non-superimposable with one another because look at what happens if I try to overlay the 2 molecules with one another. When I try to superimpose them with one another, what we end up seeing is that although, yes, the red and the red line up with one another, and at the back of the molecule, brown and brown line up with one another. Over here, we have that blue and white are going together, and here, blue and white are going together, right? And so this is not superimposable. And it does not matter how I twist and turn the molecule, I can never make this work. I can never make the 2 molecules line up with all of their atoms in the exact same place. It's important for you to have the carbon attached to 4 different things because it's the only way that you're going to be able to get non-superimposable images. Like, let's think about what would happen if our carbons were only attached to 3 different things. I'm just going to make a switch here and replace the blue with another white. So now what that means is that each of these carbons is only attached to 3 different things. All right, so now I have my 2 carbons and they're each attached to 3 different groups, red, brown, and then whites. What I notice is when I have this molecule and its mirror image, right, white goes into white, brown goes into brown, so that's the mirror image here. When I go to superimpose these molecules on one another, they line up perfectly. The reds go together, this white and this white go together, white and white go together, brown and brown go together, right? So the molecule is superimposable with its mirror image when it's attached to 3 different things, but by having 4 different groups, you end up with a molecule that is non-superimposable with its mirror image. So that is a very important thing to take note of. We want to look for a carbon that's attached to 4 different things. At this point now, I'm going to pop out of here so that I can focus on the slides and work through some examples. All right, let's take a look at some examples of molecules that are optically active and contain chiral carbons. The first one here is bromochlorofluoroiodomethane. So our carbon atom here is attached to 4 different things, right? A fluorine, a chlorine, a bromine, and an iodine. Because this carbon is attached to 4 different groups, you would say that this is an asymmetric carbon. We denote asymmetric carbons in molecules by using a star to indicate that we have a chiral or an asymmetric carbon. Now, you do not need to have functional groups in order to have an optically active molecule. It's also possible to have optically active hydrocarbons. And an example of that is shown here with 3-methylhexane. Again, the star indicates which of the carbons is chiral, so it's this one located right here. And this carbon is attached to 4 different things. In order to see that, first of all, it's helpful for us to put in the implied hydrogen that's here. Because right now there are 3 bonds shown to this carbon, and that means that there has to be a 4th bond that's to an implied hydrogen so that you complete the octet rule and show 4 bonds to all carbons. Now we can go through and look at what all the different groups are that are attached to this chiral carbon. What we have is a hydrogen, so that's one type of thing. We also have a methyl group, so that's a second different thing. We also have over here an ethyl group, so that's a third different thing. And then over on the right-hand side of the molecule, you have a propyl group that's over here. So that's 4 different things that are attached to this carbon atom. And it is really important to look at the entire group that's attached to the carbon. So here, I'm not just saying, oh, we're just going to look at the first atom. It's a carbon. This is a carbon. This is a carbon. So they're all the same. You have to look at the carbon and everything that comes after it as well. That's how you're able to determine that you're attached to 4 completely different groups. So here we're attached to a hydrogen, a methyl, an ethyl, and a propyl. Those are 4 different things, and so that's going to make this carbon atom chiral, or asymmetric. Now I want you to get some practice with an example here. I want you to determine which of the following molecules can have optical isomers. Which of the following molecules has an asymmetric carbon? So go ahead and draw the structures for these molecules, and then figure out what the answer is, and on the other side of the question, we'll go over it together. All right, I just moved things around a little bit to give a little bit more space so that I could draw in these molecules. The first one we have here is ethanal. So for ethanal, we have 2 carbons and the aldehyde functional group. Now we can figure out what atoms are attached to each of the 2 carbons and see if either one of them has 4 different groups on it. So for this carbon that's on the left, that's attached to 3 implied hydrogens, and then it's attached to the carbon that's part of the aldehyde functional group. So this carbon over here on the left is only attached to 2 different things. It's attached to hydrogen, and then it's attached to C double bonded to an oxygen. Those are only 2 different things. So that's not going to be asymmetric. Now what about the other carbon that's part of the aldehyde functional group? So in this carbon atom, it's only going to be attached to 3 things, right? There's 1 implied hydrogen here, and that now shows 4 bonds on this carbon, right? 1, 2, 3, 4. And so this carbon atom here that's part of the aldehyde functional group is only attached to 3 things. Importantly, any carbon that's on a double bond can never be asymmetric because it will at most be attached to only 3 things, right? You can't be attached to 4 different things when there's like a double bond there. So that's not going to be an asymmetric carbon either. This is only attached to 3 different things. All right, so what about 2-propanol? We'll go ahead and draw the structure for that. So we have a chain of 3 carbons, and on the second of those, we have an OH group. Now we can go ahead and put in the implied hydrogens. So for the terminal carbons, they're going to each be attached to 3 different hydrogens. And then for the carbon that's in the middle, it already has 3 bonds shown, and so that means that there's going to be a 4th bond to an implied hydrogen. Now, for the carbons that are on the ends of the molecule, they're attached to hydrogen and then whatever the rest of the molecule is. It's only attached to 2 different groups, right? Because there is really no difference between all 3 of the H's. Those only count as one type of group. So that's what we have here, and that's also what we have here on that one. Now, what about the carbon that's in the middle of the molecule? So for the carbon that's in the middle of the molecule, it's attached to an OH, so that's one type of group. It's attached to an H, so that's a second type of a group. On the left-hand side, it's attached to a methyl, so that's a third kind of a group. And on the right-hand side, it's also attached to a methyl, so that is a repeat. We're only attached to 3 different things here, OH, H, and methyls. And so that means that this carbon is not going to be asymmetric either. This is on 3 different. Okay, what about 2-pentanol? We'll go ahead and draw that. In 2-pentanol, we're going to have a chain of 5 carbons, and we're going to put an OH group on the second carbon. Okay, we can go ahead and put in the implied hydrogens. Now, I'll point out that for these terminal carbons, once again, these are not going to end up being chiral because you're going to be attached to 3 H's, right? And so 3 of the same thing. You're not going to have 4 different groups there. Additionally, for this interior carbon, that's going to be attached to 2 implied hydrogens, so that's 2 of the same thing, so that's not going to work out. The same goes for this interior carbon as well. But what about the carbon that has the OH functional group on it? That has one implied hydrogen on it, and so now we can go ahead and try to do a count to see how many different groups are attached to this carbon that has the OH group on it. Here's one type of group with the OH. We also have a second different thing when we look at the H that's attached. We also see a third thing when we have a methyl group over here on the right-hand side of the molecule. And then when we look at the left-hand side of the molecule, we see a chain of 1, 2, 3 carbons, and so that's going to be a propyl group. So that is 4 different groups. And so that is going to be an asymmetric carbon. This has 4 different groups. So this is asymmetric, and you can denote this with a star. So that's one possibility here. So what about 3-pentanol? Well, we'll go ahead and draw the structure out here. We need a chain of 5 carbons, just like that. And on the third, we'll put an OH group. All right, now we can go ahead and put the implied hydrogens in. And when you do that, you're going to see that there are 3 implied hydrogens on the terminal carbons, right? So 3 of the same thing means that those are not going to be asymmetric. And then for the second carbons in the chain, those each have 2 implied hydrogens on them, right? So that's 2 of the same thing. So that's also not going to be asymmetric. For the carbon that has the alcohol functional group on it, there is 1 implied hydrogen. And now we can start doing a count here. So what we see here is that we have an OH group, so that's 1 thing. We have an H, so that's 2 different things. Then on the left-hand side of the molecule, we have an ethyl group, right? That's a chain of 2 carbons. On the right-hand side of the molecule, we also have an ethyl group, right? It's a chain of 2 carbons, and then that's it. So here, this carbon atom is only attached to 3 different groups. Therefore, this molecule does not contain an asymmetric carbon. This molecule will not be chiral. It will not have optical isomers. And there we have it. The only one that will is answer choice C, that is 2-pentanol there, because it's that second carbon atom that is asymmetric. That brings us to the end of this video, and up next we're going to talk about polymers.